Greetings, pre-calc students. This is Mrs. D, here to talk to you about rational functions, particularly their asymptotes and intercepts. Look at that lovely rational function. That is not our parent graph, but it's pretty darn close. That is the reflection of our parent graph. And I'm noticing that it has asymptotes at y equals 0 and x equals 0, even after that reflection. Cool. Rational functions, also known as reciprocal functions, oftentimes have both vertical and horizontal asymptotes. Tell me more, Mrs. D. Here we go. Intercepts. Functions, most functions, not all, will have intercepts. There are x-intercepts and y-intercepts. A function that we're not familiar with is showing here, but notice it has an x-intercept somewhere about there. I would call that point x0 because it is on the x-axis. I have traveled some negative distance in the x direction, and I have traveled 0 units in the vertical direction. There I am on the x-axis. This function also appears to have a y-intercept, only one, right about there, to the best of my drawing abilities. I will call that point arbitrarily 0y. I have traveled 0 units in the x direction and some arbitrary positive number of y units in the vertical direction. There I am on the y-axis. So in order to find an x-intercept or a y-intercept, those two facts can be extremely useful to us, and I've written them there in arbitrary format for a reason. Let's look at the function, the linear function, 5x plus 2. This function has an x-intercept and a y-intercept because it is a line that has slope. Vertical lines, horizontal lines may or may not have both intercepts, but this one will, rest assured. So for the x-intercept of this function, it is some point, recall, x comma 0. That means the output of the function is 0. And I'm trying to find that input value, that x value for the x-axis, the number of units that I travel in the horizontal direction. I can simply solve this equation, and you could do this with any function, of course. That output would have to be 0, and the input apparently here, not so obvious, is negative 2/5. Now I'm not just going to write negative 2/5. I'm going to label that as a coordinate. Negative 2/5, 0 is the x-intercept of this graph. It is a location on the x-axis. Notice what we did there to find the x-intercept is we assumed that the output of the function was 0, and we determined the x or x values that gave us that output of 0. Here there was only 1. We'll use the same function to find the y-intercept. And maybe you all know the form of this function, the way that it's already written, but just humor me and follow along here. We're finding the y value, the arbitrary y value, where the input is 0. So x is 0 in this case. What value of y? How many units am I traveling up or down to get this y-intercept? And the answer is 2. But again, I'm not going to write y equals 2. That might even be misconstrued as a horizontal line. The y-intercept is a location on the y-axis. We'll label it as a point, 0, 2. Notice once again the input is 0, and the output is that value. You should only have one y-intercept for any function. Here we have some rational functions. They are relatives of the parent function 1 over x. They definitely don't look much like it, but we see the fractional setup here, and we can find the intercepts for these functions. Here we go. We will start with, I think the y-intercept is usually a little easier to find, because there you have that input of 0, and you're trying to find the output. So inputs of 0 are pretty straightforward. 2 times 0 divided by 0 squared plus 3. I've got a nice 0. That's not a nice 0. There, that's better. Divided by 3. Can you divide 0 by 3? Certainly, you get 0. Looky there, that graph passes through the origin. Let's find the x-intercept. The x-intercept is where the output is 0. We're trying to find the x value. So this fractional function sometime will equal 0 potentially. Let's see if we can figure out when. a fractional equation set up like this, you might be frightened with that denominator. Fear not. If you multiply both sides by that denominator, it will go away because multiplying will undo the division, leaving us with 2x basically equal to, well, x squared plus 3 times 0 is still 0, isn't it? Notice here I'm just looking at the numerator. At this point, divide by 2, and lo and behold, you get 0 again. Makes sense. 0 is a point. The origin is a point on the x-axis and y-axis. It's where they intersect. G of x might not be so simple. We're going to start again with the y-intercept. With that input of 0, we'll see what the output we achieve is here. So 0 squared minus 2 times 0, take away 3, all divided by 2 times 0 squared. You get the gist, I think. That will give me the output, the unknown output. All those zeros essentially give us 0. Take away 3 is negative 3 in the numerator. 0 plus 8 in the denominator is negative 3/8. That is your y value. But again, we're not going to leave it like that. It's a point. It's a location. 0, negative 3/8 is the y-intercept. The x-intercept for this function, it will be the point where the output is 0. We're trying to determine the input, or the x value. So once again, I have this fraction, this function that's represented in fractional form, and I'm trying to determine what makes it equal 0. Once more, if you multiply both sides by your denominator, you no longer have a denominator. Multiplying will undo division, and we're left with 0 equals x squared minus 2x minus 3. Here's a thought. The only way to get 0 is to take, in fraction world, right, is to take 0 divided by a number, any number except 0. 0 divided by any number will give you 0. This is the reason that we're now just focusing on our numerator. Just like before, we were just focusing on the numerator. 0 divided by anything other than 0 will give us 0. Here I can factor. This is quadratic. Look, we're going to have 2 x-intercepts. Woohoo! If I factor, I will see the 2 factors. I'm still trying to find out when it equals 0. One x-intercept will be 3, 0, and the other x-intercept will be negative 1. These are the values of x. They make the output 0, and there happens to be 2 of them. Now on to asymptotes. Every reciprocal function has potential to have both a vertical and a horizontal asymptote. The parent function has asymptotes, as we saw on the first screen, at 0 for x and 0 for y. The vertical asymptote, if you need a reminder, for any reciprocal function, the reciprocal function kind of presents itself as one function divided by another function. When you're trying to find the vertical asymptote, really you need to narrow in and focus on that denominator. Don't ignore the numerator for the possibility of holes, but whenever this denominator is 0, those values of x become or are your vertical asymptotes, because then the function will be undefined. You're trying to divide by 0, and that is not something that is realistically possible. Those are the values of x that give us the vertical asymptote. We've done that before. Here's the brand new exciting thing, horizontal asymptotes. Now keep in mind not every function will have a horizontal asymptote, but if it does, what we're doing is we're expressing the end behavior of that function. We are looking at what happens with the outputs as the inputs, or x, become very large. Analytically, what we're going to do is see what happens as x approaches infinity. Now, mind you, you cannot substitute infinity for x. You can't plug in infinity and say infinity plus 1 divided by infinity minus 3. That's hard for the human mind to wrap around. So what we're doing is we're actually calculating a limit as x approaches infinity for our function. And if that function equals some number at infinity, then we have found the horizontal asymptote. Now, the how-to on this, maybe this would be a note worth writing down because Mrs. D didn't type it in here. How are you going to do this limit calculation? This special limit calculation will require you to divide every single component of each function in the numerator and the denominator by the highest power of x. And that's the highest power of x within the entire function. Numerator and denominator both considered. Okay, we'll see how that works out on the next slide here.